We are live.
Good evening, everybody. I welcome you all to today's iFocus online lecture number 529. Currently, we are running in the new topic that is optics and refraction, module 4. Today, we have Dr. Garvita ma'am, associate consultant at Center for Sight Eye Hospital, New Delhi, who's going to talk on measurement of light, radiometry, and photometry. Welcome, ma'am. To moderate today's class, we have Dr. Kiran Kirtani ma'am. Ma'am has finished her MBBS from BJ Medical College, Ahmedabad, and MS from MNGI Institute, Civil Hospital, Ahmedabad, where she received a gold medal. Following which, she did a senior residency from DDU Hospital, New Delhi. Currently, ma'am is a senior consultant with Center for Sight Eye Hospital, New Delhi. She's a trained and certified femtocataract surgeon and a refractive surgeon, organizing secretary of prestigious PG training program iFocus, and also an organizing secretary of IIRSI. She's been a faculty with iFocus, IIRSI, and various other conferences as well. Ma'am has numerous book chapters and publications in index journals to her name. Welcome, ma'am. And over to you for the introduction of our beloved, respected Dr. Sagarika Patel, ma'am, to chair today's session, and our speaker, Dr. Garvita, ma'am.
Yeah. Thank you so much for the kind introduction, Dr. Kritika. I wish there were words enough to describe our dear, loving mentor, teacher, professor, Major General Dr. Sagarika Patel, ma'am. We are all lucky to be under her tutelage. She has done her MBBS from Calcutta Medical College, DO and MS from Army Hospital, and her glaucoma training from RPC AIMS. She's been a gold medalist, a Frankener Silver Casket for standing first in surgery in the Calcutta University, currently a senior consultant at Center for Sight New Delhi, and our dear mentor. Served as the Assistant Chief of Integrated Defense Staff Medical at Army Headquarters Delhi, HOD of Ophthalmology at Army Hospital and Army Base Hospital Professor at AFMC Pune. She's been the only lady officer to have commanded the world's highest general hospital at Leh, where she was instrumental in establishing telemedicine nodes in high altitude to help soldiers stationed in the highest battleground in the world. Going to the next slide, please. Ma'am has received the Vishesh Seva Medal in 2016, Sena Medal Distinguished in 2014, Chief of Army Staff Commendation 2004 and 2011, amongst other prestigious awards. Active in research, has over 78 publications with 278 citations in both international and national peer-reviewed journals. She has written chapters in books and has edited a book, Resolving Dilemmas in Perimetry, Resolving Dilemmas in Ophthalmology, and has held innumerable instruction courses in national and international conferences, especially in glaucoma and myopia. Recognized as a supervisor to guide PG and diploma students, UG and PG teacher and examiner, she has also served as NCI inspector for MBBS DNB, National Faculty for Glaucoma, faculty endorsed PG training programs, and in iFocus. She has been serving as a reviewer for the MAJFI Index Journal, Journal Clinical Ophthalmology Risks, and DJO, MDPI, and Curious Medical Publishing Online Journal. Now, coming to our dear and dynamic Dr. Garvita Dabas. She did her MBBS from DY Patil School of Medicine and MS with a gold medal from Muzaffarnagar Medical College and Hospital. Having done a fellowship in cataract and refractive surgery right in Center for Sight, New Delhi, she has been a bright student who has received gold medal in FAICO. Currently, she is working as associate consultant at Center for Sight, New Delhi. She's been, at this young an age, a recipient of various prizes in photography, paper, and poster presentation in many conferences, having authored already over 8 journal articles and delivered 6 instruction courses and over 30 presentation and lectures at various ophthalmic meetings, national and international. She's been co-author already of 4+ chapters. We are very proud of her. And this is a very difficult topic. And I'm sure Garvita will make it easy for all of us. And in the end, Sagarika ma'am, with her, wits, wisdom, and pearls, will be able to enlighten us on this topic further. Over to you, Garvita. Ma'am, would you like to say something for the introduction?
Yeah, thank you so much. These are very difficult topics, and tell the truth, none of us has ever studied this very thoroughly. In fact, I feel that Garvita is going to enlighten all of us. And we all are here to learn, whether it's with gray hair like mine or with the young black
Gray
hair
hair
that
like
you all
mine.
have. But it is very good. Topics are coming up which we had never even thought of, which we probably must have just glossed over in our in our books. So I invite, and I'm very, very happy to note that Kiran, you have a gold medalist, another Krutika, one of our own fellows who's done so well, Garvita, another of our fellows. We are all there in the same page today. I mean, it's an honor for me. It's an absolute honor for me. And I won't waste your time, Garvita. So, Garvita, I think, what we will do is that when you finish speaking, we can just have a small discussion on what are the clinical implications of this particular thing so that we all learn. See, I'm telling you that most of us have not even read these chapters. So it is very important for us to learn from each other. So I invite you to please go ahead and speak, and we would love to hear what you have to say. And thank you, Kritika. Thank you, Kiran, and for this. And for the introduction and for starting of the program. Please, thank you so much. Go ahead, Karvita.
Thank you so much, ma'am. Sagrika ma'am, Kiran ma'am, both lovely, my fantastic mentors, and also dear Kritika, who's a lovely junior to me. And I hope I will do justice to the topics, and I will just share my screen for the same. I hope my screen is visible and my voice is clearly audible.
Yes, ma'am.
Thank you. Yes. So I will begin the topic. The topic given to me today by iFocus is measurement of light, radiometry, and photometry. So starting with light, what is light? Light is an electromagnetic spectrum, and it has constitutes of various parts of the light. Correct. The human visual system, it responds to this entire wavelength of light, which starts from gamma rays, X-rays, UV rays, then comes the visible spectrum, then the infrared, microwave, radio waves, and lastly the long radio waves. This is the entire range and the wavelength of light. However, the part that is visible to our human eye is only the visible spectrum, and that constitutes from 380 nanometers to 770 nanometers of wavelength. And the reason we see light of different wavelengths and it's in a continuous range of color, that is because the visible spectrum extends from 650 nanometer, which is the red light, followed by 540 nanometer, which is the green light, further the 450 nanometer, which is the blue light, and so on. So this is our human eye. We can see the basic structure of the eye. This is the cornea, followed by pupil, followed by the lens and the iris. And this is the entire lining at the back of the eye, which is the retina. And this retina is finally, through the retina, we have all these cells where light forms and falls and activates our photoreceptors of rods, cones. Cones are in three colors, the blue cone, red cone, and the green cone. And finally, they activate the rods and cones, the photopigment layer. And finally, we are able to perceive this light. Correct. So the reason eye sensitivity to all these colors is because our cells are sensitive to all the wavelengths. Ultimately, everything depends on the wavelength that determines the eye. So there are, as I told you, there are three types of cone cells, which is the red, green, and blue range. And this is it's called the spectral sensitivity function of the rods and cones, which is why they behave and they are activated by that particular wavelength of light. So how did this come about? Like, how did we start measuring light? So in 1924, the Commission International d'Éclairage, I hope I pronounce it right, it's the International Commission of Illumination, or the CIE, asked almost 100 people to visually match the brightness of monochromatic light sources with different wavelengths under controlled condition. And the average measurements of these 100 observers was called the photopic response, which was perceived as an average human response. And based on their findings, the committee deciphered two types of responses, which is the light response and the dark response, also called the photopic response and the scotopic response. So if we look at this graph, this is a graph of where there is a measurement of scotopic and photopic curves along the relative response and the wavelength of light. So as we can see, first the scotopic graph is seen and it is followed by the photopic graph. And the curve on the right is this is the photopic ones. This is the response of human eye under normal lighting condition. And the reason it is activated is because of the cones present in the retinal pigment epithelium, because they get activated by the photopic light and they are activated by human color perception. Therefore, it is this photopic response that is responsible for color discrimination. Coming to the scotopic part, scotopic light is seen, as we can see, in lower wavelengths, which is at low level of light, the rods are activated, where they are more sensitive. Rods are more sensitive than cone to any level of light, which is why they get activated even at the lower wavelength. And also they are comprised of a single photopigment. They cannot differentiate color, which is why they are activated in this manner. So to summarize, if you look at this particular graph, the CIE 1931, 1978 and 1951 responses. So first is the dark response. This scotopic response is peaks at 507 nanometer, which is the, as you can correlate to the blue-green range, where it is activated, the scotopic response is activated by the lower intensities of light. Comparing it with the photopic response, which is marked by the red, and the area underneath is the various colors, those are percepted as per the wavelength of light, we can see it is maximally activated at 555 nanometer, which lies in the yellow-green range. And also at 510, which is before and after 610, sensitivity reduces to almost half. So if we can see here, the sensitivity reduces as seen by the Y graph, and we can see at 510 the sensitivity, and at 610 nanometer again the sensitivity reduces to almost half. So maximum perception of light is in the yellow-green spectrum, which is around the wavelength of 555 nanometer. So why is this shift of sensitivity and what is it called? It is called the Purkinje shift. This shift of maximum visual sensitivity from photopic to scotopic, which is from 555 to 507 nanometer. And what happens in this? It is the red end of the spectrum that becomes relatively dull in scotopic condition due to this Purkinje shift and shortened range of sensitivity. So if we see this picture during the day, followed by dusk, and finally at night, as we can see in the daytime, the rods and cones both are picking up the color and the cones are more activated. Therefore, the red appears to be extremely bright as compared to the other warm colors. Followed by dusk, where we can see the sensitivity of the cones going down due to less visible light available for the eye. And at night, the green and the blues become dominant and there is no bright perception because the rods are activated. So finally, coming to the quantitative measurement of light, that is carried out in two ways, by radiometry or photometry. First is radiometry. Now, what is radiometry? It refers to the measurement of light in terms of power generated, emitted, irradiated. What it essentially means, it is the science of measuring light in any optical proportion of the electromagnetic spectrum. So the first light spectrum that we saw, the entire wavelength is covered, whether it be ultraviolet, visible, infrared or radio waves, everything is covered. And the measurement unit is watt. Now there are various parameters to assess radiometry. What are these parameters? First is the radiant flux. What it refers to, it is basically the amount of light that is generated from a point source. And the reference unit is watts or joules per second. So as we can see in this diagram, there are three types of figures here. First is the laser beam, the entire light that is being produced being detected here by the detector through the aperture. Second is the fiber optic. Fiber optic cable produces point source of light, that is read by the detector, followed by a focused beam of light through a lens that is focused on the detector. So all of these parameters are giving you essentially the flux of light, which is the amount of light emitted from the source. So this is applied in LED lamps, fiber optic cable, and all such sources. Next is radiant intensity. So we know radiant flux refers to the amount of light generated, but this light that is generated, what's the amount of it? What is the intensity of this light? So the measurement unit is watts per steradian. What is steradian? I'll just explain it to you. So as you can see, just draw an imaginary 360-degree sphere around a center source of light. Let's say this candle wave flame. So if we see, imagine this sphere around it at an particular angle, there is a conical shape that is projected at a particular angle. Let's call it omega angle. So this entire area is called the steradian, which is a solid angle of a cone with apex at the center of the sphere, which is the source of light, and that cuts off the area on the surface of the sphere, which is equal to twice the amount of the radii. So r square, radius of the sphere, twice that amount is the area of the sphere, and this entire angle is called 1 steradian. So a solid angle is area divided by r square. This is a single steradian. So if we come back to this intensity area, if you look at this sphere, the center is the source, and the intensity may be studied by the amount of light emitted from a source in one particular angle, which is watts per steradian. So this type of testing is done for small sources of light when we are studying it in one particular direction. For example, LED lights, infrared lamps, or UV lamps. Coming to the next part of it, which is the irradiance. We have already studied the light produced. We have studied the intensity of that light produced. So the next part of the study is how that light is falling on the surface. That is called irradiance of that surface. And of course, it is measured per area, which is watts per square meter. So 1 by 1 meter square, the amount of light falling on that meter will be the irradiance of that light on that area. So it is applied in fields of remote sensing, biological and medical sensing. The final part to it is radiance, which is, now that we have studied light falling on a surface, light gets reflected back also. So what is the amount of light that is reflected from that surface, which is watts per steradian, as we studied about the intensity per square meter. So that is the unit for radiance. And it is studied with a radiance meter, and that gives you the particular direction in which the light is delivered, as well as the reflection of that light, which is the radiance. This is important for night vision, avionics, and remote sensing. So what is photometry? Photometry is again the measurement of light, but it does not read the entire spectrum. It only reads the visible light, and also it is weighted according to the human eye. So it is a quantitative sign which is based on the statistical model of human visual response. Of obviously only the human eye is seeing it, so therefore only the visible light is measured with photometry. Again, similar to radiometry, photometry also has luminance flux, which is the amount of light produced in all directions, and the measurement of unit is lumen. Then comes photometry, where luminous intensity, just like we had intensity in the radiometry, similarly we have luminous intensity. It again refers to the light emitted from the source, but in a particular given direction, and the unit of light is candela. So originally this was called candle power. Why? Because at that time the source of light was a candle flame. which was a standard wave candle. So at present, that has been changed to candela, which is the modern unit, and it is based not on the candle flame, but a standard electrical filament lamp. So one candela is 1 lumen per steradian. I will just show you a picture to explain. So this is the sphere, and at the center is again the point source of intensity. So if as we know, the point source of intensity, the unit is 1 candela, and this entire angle cone of unit solid is steradian. So this amount of light that is produced will be 1 lumen, which is luminous flux, right? So a point source of 1 candela is almost around 4 pi. Now 4 pi steradian is the amount of area around the light. So the mathematical formula is luminous flux given by the Greek letter phi equal to 4 pi I. I is the intensity. So if we look at this picture, luminous power is 360 degree, luminous intensity in one particular angle, and 1 candela of luminous intensity will emit 1 luminous flux into 1 cone, which is 1 steradian. Okay. So this is an overall idea of luminous flux given by the symbol phi with a metric unit of lumen. Now, if we look at this eye picture of luminant intensity, it is 360 degree sphere given by one solid angle. Then comes illuminance, which I will now describe. So illuminance again that refers to the light falling on the surface, which is why it is the number of lumen per square meter incident. There were old names like lumen per meter square, which is meter candle, or lumen per foot square, which was foot candle, or lux. So the mathematical formula to derive illumination is E equals to intensity I cos I upon D square, where I is the luminous intensity and D is the distance of the surface from the light source. So if we look at this picture here, to study it more clearly, if you look at, this is a practical example. If you see this second picture, this is the shower head and this is a bucket. So the total flux is the lumen of light produced, and the light that falls on the surface is lux, which is illuminance of the surface. So again, if you look at this E picture, where it is illuminance, that is lumen of light falling on the surface of 1 lux. So that is the unit of illuminance. If it is in feet, that is given as foot candle. Finally, coming to luminance, which similar to radiometry, if a light falls on the surface, it has to be reflected or emitted back. So there are two types of units that are used in luminance. One is Lambert, which is defined from a perfect diffuser surface, which is 1 lumen per centimeter square, or foot Lambert, which is called luminance of a surface reflecting or emitting 1 lumen plus feet square. Finally, coming to the apostaples, which is used in HVF and the visual fields analysis. So one apostolepse is given by ASP. It is also a unit of luminance, and one ASP is a reflection of 1 lumen of flux per square meter. So this is an average chart of relative luminance chart where you can appreciate the luminance value uh, across the universe, because sun has almost 900 million luminance, followed by the tungsten filament, followed by, if we come down, we can see at 30, we have white paper in good reading light, followed by neon lamp. Point 3 is almost one quarter hour after sunset on a clear sky. 0.03 is how snow appears on a full moon light. Then 0.003 is on a fairly bright light, followed by the darkest, which is 0.0003, which is the threshold of vision. Finally, what is brightness? Brightness is not a very scientific term. It is not precisely described, but in general, it refers to the sensation of light given by illumination on the retina. And as I already shared, apostlip is defined as luminance of a perfectly diffusing surface that is emitting or reflecting 1 lumen per square foot. And as I said, that is the illumination we set in the human visual field test, where the targets are often specified in apostibles if you see the report. So coming to what is the difference between luminance and brightness. As I said, brightness is a very subjective term. Or lumens, however, is something that we can measure in an objective manner. There is a law that refers to the difference between the two, which is the Weber-Fechner law. It defines that two bodies with the same luminance can have the same brightness. But if one of them has double luminance, we cannot say the brightness is said to be doubled, because they are brightness is a subjective thing. It does not follow a hand in hand direct proportionate law. So in simple mathematics term, if L is a value for prevailing luminance of a surface and dl is the minimum noticeable increment, so every dl by L is a constant. Like every rate of change of luminance is supposed to be a constant. Again, this is an example of luminance and illuminance that we just read. So luminance, the surface of the sun is 2 into 10 to the power 9. White paper in sunlight is 2.5 into 10 raised to the power 4. TV screen white is only 100. White writing paper in a classroom is 70. And as I already said, white paper in moonlight is very low, which is 0.003. So now coming to illuminance, which is lux. Bright sunlight, again 10 raised to the power 5, and on a full moon night it falls to 0.2. So what are the clinical application of illuminance? So in operating theaters, we have to keep the illuminance up to 50,000. For a drawing office, 750, supermarket, 500, library reading area, 350. For an eye surgery, it has to be a minimum of 1,000 to 2,000 lux. So coming to the fundamental laws of photometry. Law 1, it is called the inverse square law. What it means, it's illuminance that is on a point at a surface that we see in the picture is inversely proportional to the square of the distance between the point and the source. So what if we see the picture, we see the light source that produces light in lumens, followed by lumens per solid square in steradian, which is the candela. This is per steradian, the cone angle that is formed. The d being the distance till the surface. So we can see that E is equal to I, which is intensity, divided by square of the distance between the source and the surface. So the more the distance is, the more the illuminance will reduce. The second law is that if a perpendicular or a normal is drawn at the illuminated surface, and let's call it angle theta, to the direction of the incident light, then the illuminance is proportional to the cos angle theta, and again it is divided by the r square, which is the radii of the steradian. So the further the distance is, the lower the illumination is going to be. Coming to the another term, which is Troland. What is Troland? It is a unit of retinal illuminance. What it means, if the pupil size effectively is 1 mm of pupil area, the views on the surface, and it views a surface having lumination of 1 candela by meter square. So that is 1 Troland of retinal illumination. The amount of light emitted from or reflected off an object is called its luminance, and that is commonly into a layman called brightness. Illuminance refers to the amount of light that shines onto a surface measured in lumens. Coming to contrast sensitivity, what is contrast? It has two objects to it, subjective and objective. So subjectively, when we do contrast sensitivity, it can be described as appearance of two areas of the visual field which are seen successively or together, and any difference that is observed will be a combination of the brightness or the color. Objectively speaking, if L refers to the luminance of the area, so L1 minus L2 divided by the L1, which is considering we have two areas of visual field to compare, that will give us the contrast value objectively of the two areas in the visual field that we are considering. So to summarize the entire thing in unit value, radiant, the flux, the amount of light in the entire spectrum of electromagnetic wave is given by watt or joules per second, followed by luminance flux comparatively, which is given in lumens. Radiant intensity, which is the intensity of the light that is produced, is watt per steradian. And if we consider the luminous intensity, it is candela per steradian. Irradiance, amount of light falling on a surface, is watt per square meter. Illuminance, the amount of light on the surface, is lux per meter square. Radiance is watt per steradian per meter square, and luminance can be calculated as apostolic, which is 1 per pi and candelas per square meter, or foot Lambert, which is 1 pi candelas per square foot. Square foot becomes foot Lambert. So again, this is a pictorial demonstration of both the things together. So if you look at the source power, the source is producing light. If you study the entire electromagnetic spectrum, we look at radiometry. If we look only at the visible part, that is luminous, which is photometry. So the amount of source that is producing power in watts, that is radiant flux. And if luminance is luminance flux given by lumens, directionally when it falls on a particular solid through a solid angle, the intensity is watts per steradian for radiometry, whereas it is lumens per steradian or candela for photometry. And if it falls on an extended source, that is, if it's reflected back, it becomes watts per meter square and candela per meter square for photometry. On a given particular area when it falls, this is watt power per unit area, that is watts per meter square, which is called irradiance in radiometry, and illuminance in photometry, which is lumens per meter square, also called lux. So again, if this is the sun and it's producing light, which is in the form of luminous flux, which is given by lumens, a single angle, that is steradian angle, that is formed is the luminous intensity, which is given by candelas. And this intensity of light again falls, let's say, on the moon. So that is the illuminance of the moon, which is given by lux. And as humans on earth, we get the reflected light into our eyes, correct? And that reflected eye through the pupil area, if it is 1 mm square, that is the luminance that we receive given by candelas per meter square, and ultimately it activates the retina. So the retinal illuminance is measured in terms of trolets. So this is an entire summary of how radiometry and photometry work together. So just again a brief idea, the radiometry units and photometry units we have already discussed, but just to re-establish the SI units because they're very confusing. So again, quantity of light produced, radiant flux. In photometry, luminance flux. Amount of light, the intensity studied per unit solid angle or the steradian is watts per steradian, and luminous intensity again 1 candela, considering its candle power now. Then quantity of light incident on a surface that falls onto a surface is irradiance, which is watts per square meter. And again in photometry, it is illuminance per square meter, which is lumen per square meter, also called lux. Now the light reflected or emitted back per unit area per solid angle, that is watts steradian per square meter by radiance. In photometry, it's called luminance, a 1 foot candle, which can 1 apostolic or 1 foot Lambert. Then finally, illumination of the retina is retinal illuminance, and there is no radiometry because it can only perceive visible light. So therefore, it's a photometric measure called Trollens, which is 1 candle per square meter viewed through 1 mm square of size of pupil. So finally, the difference between radiometry, photometry. Radiometry is electromagnetic radiation. This is photometry is visible light perceived by human eye. Power per unit area, irradiance, illumination. This is radio waves, gamma waves. Radiometry involves everything. Visible light only seen in photometry 400 to 700 nanometer. Radiometry measured by total power output, whereas photometry is measured using spectral distribution, color of light, intensity of light, and units is watt per square meter, and in photometry lux is given. So now coming to the applied aspects of light. So why do we have to measure the light? Why is it so important? Because we have to establish safety legislations by the employers to provide sufficient lighting for standard purposes. Now that can benefit in terms of reduction in eye strain, fewer accidents, better working condition, greater productivity. Coming to ophthalmology specifically, we have the visual acuity testing where luminance of 220 to less than 1 candela per meter square is given. Then we have visual fields where the background is 31.5 apostolypse and light stimulus is 0.8 to 10,000 apostolypse, followed by color vision where we have the FM hue test where color vision is assessed as in various light. ERG, where stimulus strength and background illumination is set to 3.43 and 17 to 34 candela per meter square. Finally, in tests like VEP, we have to study the luminance of stimulus, which is 80 candela per meter square. So that is all from my side. I hope I could shine light both radiometry wise and photometry wise to this very short and very scientific topic. And I hope I could do justice to this.
Yes, absolutely. It's a very, very difficult topic, actually, and involves a lot of principles of physics, and it's very difficult to understand also. But very nicely, you have compendiumized it in such a way that it has been easy for me, or I'm sure for all the students, all the more because they are more, bright and active when it comes to learning, that this topic has been made interesting by you. So, pardon me if I'm wrong, but just to summarize, the total amount of light which is coming out from any electromagnetic source is called radiant flux, which is measured in watt.
Yes.
Whereas if it is coming only from in the visible spectrum, which will be measured by photometry. So any electromagnetic spectrum will be measured by the radiometry. However, the visible spectrum will be measured by the photometry. So there are four main parameters as much as I could learn. The first one being the total amount of light which is coming or electromagnetic rays which are coming, measured with lux oblique lumens.
Yes.
And then it comes to what is the amount of light which is going in a particular direction. That is the intensity of the light, which will be measured by radiant intensity versus luminous intensity. The units being watt per steradian or lumen per steradian, which will be also called as candela, if I'm not mistaken.
Yes.
Correct me if I'm wrong. And the amount of light which is falling on an object will be, or electromagnetic wave which is following on an object will be measured by irradiance versus illuminance, measured in watt per square meter or lux lumen per square meter.
Yes.
And the amount of light which is being reflected from the surface will be measured as radiance versus luminance. Radiance measured as watt per steradian per square meter, and luminance as apostolypse, that is candela plus per square meter or foot lambert. Am I right?
Yes, very well summarized.
So interestingly, to think of it, it's very interesting to know that both radiometry and your photometry have very important ophthalmic applications. So all the laser systems which we are using in our day-to-day life, day-to-day work, be it retinal lasers, be it lasers we are using for glaucoma, be it photoablation, be it photo disruption, be it photocoagulation, all of these are eventually being measured for their optimization in terms of their uh, power, that is the wattage that they're producing, to the laser tissue interaction, to the safety protocols with the help of radiometry,
Yes.
right?
Yes.
And photometry has been very, very helpful for us in defining how we measure, or rather refining how we measure the visual acuity of the patient, the wave spectrum or wave front of the patient, and also in deciding what is the amount of lighting which should be present in a particular environment, especially the surgical environment where we are operating. Also in day-to-day activities, there is an importance of the amount of radiance which is coming, or rather the luminance which is coming, because that determines the fatigability of a person in a work environment. So in
Yes.
office spaces or in workplaces, there are specific guidelines which have been given across the globe, and like in India also by associations like IIOH, where they give specific guidelines of what is the correct amount of illumination which is to be used in office spaces for people to feel most comfortable with least amount of fatigability, right?
Yes.
So I think it's a very interesting read for all of us. Ma'am, what would you like to say? And please add the words of wisdom, yeah?
No, no, it's first of all, I must say that Garvita, you have, given a very difficult topic, which is actually very, very, it has lots of physics in it. But the way you've put it, I think all of us have understood, and Kiran has summarized it most beautifully. So I'm going to just add a couple of things to it. The first of all is that let's say, for example, let's consider the basic epidemic which is going on. That is myopia. Do we realize that it is the light, the LED lights, which are possibly one of the factors which is also responsible for increasing our myopia? That's one. Number two, that the amount of light which is present in classrooms has been also a factor responsible for increasing myopia in children. That means in a classroom, if the light is poor, just Kiran, as you've just talked about it, that if the light is poor, remember your myopia is also going to be increasing. Next is the moment the child or a patient enters our IOPDs, or if a person is visually impaired, we always tell the person that please definitely have enough light for that person, so that the visual impairment will be decreased if the amount of light that is there is good. So that is one very practical point of great practical importance. That means the amount of light for a visually impaired should be more. Now, there, Garvita, I was just, thinking in my mind that we have got to talk about illumination of the surface, intensity of light. All this comes, of course, we won't go to the physics of it, but that is important for us. We enter into our refraction chambers. Over there again, the illumination of that chamber, it has to be dark, but the light that is present in the digital system where we are asking the patient to read has to be of a specific amount, so that many of sufficient luminance so that the patient is able to see. So everywhere that we look and in ophthalmology, which Kiran was pointing out, we have got these particular factors playing in the background. And most of us don't understand these terms. Like, say, for example, the Humphrey perimeter, which we all are conversant with, apostomes. Why apostomes? Because what is this illumination of what is this particular unit of light? What do you mean by decibels, etc., etc.? So, today, Garvita, you have brought across some points by which we have been able to differentiate that, this is important. For example, now you talked about lasers. Every part of your lecture has got huge clinical applicability. And I think next time when we go into our chambers, we will sort of think about Garvita's lecture that okay, she said this, this is the meaning of it. But this has got great practical importance. Great practical importance. Practically all our systems, we begin from the digital, I mean, our screens which are there. We begin and to our lasers, to our imaging devices. Everything, the illumination becomes very important. How much of light is coming out, how much of that 1 millimeter of light which you talked about and through going through the pupil. I think that was, I mean, it just made me really wonder that just imagine, even if you have a pupil which is this small, that also. So just imagine if a person has got two pupils and that, let's say, we have made an iridotomy which is present slightly below where the light can also enter. So you have a normal pupil and you've got a pupil which is just about a millimeter, So the amount of light that is going in, which may hamper or cause problems to the patient. So all this has great practical importance. And I really thank you, Garvita. Of course, I'm not going to take away the words from Krutika. So, but I think it was very, very, very illuminating and your lecture was very good.
Thank you.
Really enjoyed it. Just as Kiran said, very nice.
Thank you so much, Garvita. I think with your radiance, we have all been, or rather your own, with your lux, we have all been now able to give back the, luminosity that you have so nicely given away to all. I would also request Kritika to take up any questions if are there. And if at the back end we can find out that actually there have been questions which have been asked to the DNB students in any of these exams on these particular topics, or if we are able to find out any short questions or long notes which have been given, we will be definitely commenting upon them subsequently in our in the lecture that you have just given, so that the students are aware that if a specific question is asked in this particular topic, how are they supposed to answer or how are they supposed to write about it? Am I right, ma'am?
Yeah, I think so.
Yeah,
So
so
actually, if you ask me, ophthalmology is such a huge, huge topic, and every part of it, has got a certain amount that they can only ask about. But I think what is very important is the understanding. Today's lecture has gone into understanding these terms. Apostolps. I mean, like people just get foxed. What is apostolps? It's only when we read Reddy's book then we come to know what is apostolps. Then we'll talk about luminance. We talk about color blindness. We talk about all is the various blood tests which are done for color blindness. Each of them, each of this, the photometry which is talked about has so much of importance and clinical implications in each of our features, the things that we do in ophthalmology. So I think the practical importance of this lecture has been tremendous because she's made everything so clear that, this is what a candela is, this is what a lux is, this is what illumination is, this is what photometry is. You're not looking at the radiometry, you're looking at photometry. Fabulous.
right. Dr. Kritika, would you like to add something here?
Ma'am, we don't have any questions, but congratulations and thank you, Garvita ma'am. You have simplified a complicated topic to a very great extent, especially adding those animated pictures. It has given us a picture memory, which we'll never forget. Like if we go anywhere, we'll remember that picture and will not forget those terms at least. Thank you so much for those at least, ma'am.
Thank you,
Right.
ma'am. Thank you.
Yes. So, Garvita, this has been very inspiring lecture for everybody. And, we'll all have to raise our standards very high now because you have made a difficult topic so easy for everybody that now the easier topics will have to be worked up much harder. Right.
Thank you for the kind words, ma'am. Thank you to also the iFocus for this platform. But thank you so much, dear mentors, for such encouraging words.
All
No,
right.
you've encouraged us.
That's true. That's true. All right. So, Kritika, if we have no further questions, what is your suggestion?
Ma'am, we can call it a day, ma'am. We don't have any questions.
Yeah, because the topic, if there are any particular or further questions, especially, I mean, I was always fascinated by especially when it comes to perimetry. My simple question to Sagarika ma'am here will be the aposlips that are being described. What is the practical or clinical implication of observing what is the sensitivity or, the aposlips which are mentioned or the decibel values which are mentioned on the perimetry? In just a nutshell, if you could just let us know, ma'am.
Yeah, sure. So it's just this that, apostrophes is a very large number. So it comes in thousands. So you can't put that entire thing. So what they do is they put filters and decrease the amount so that you can make it into a smaller number. That's why we see that amount of stimulus of the light intensity which is being seen by the patient that comes in decibels. So that is apostrofes has been converted into decibels by means of filters so that they can decrease that amount of the numbers that which come over there. It's just that.
And the pictorial representation of the same is easy.
Yeah, of course, because you can't put those numbers. Let's say, for example, when you're looking at a raw data of the of a printout, then in that case we are able to see 32, 36, or 24, 28. But that with the numbers which comes in apostles becomes too big. That is why. So actually, Garvita and Kiran, Krutika, all of us, we realize that light. We just talk about light, but we don't understand what light is, the composition of light, how each part of it is affecting us. Wavelength, we talk about wavelength. We don't understand it. We just say wavelength of light, itna light aata hai, and this is the wavelength that goes in it. But it is, the understanding today, what she's talked about, has really cleared a lot of doubts and cleared a lot of sand from our memories and from our brain. That's, I think it's very, very nice. Although, actually, to come down to the brass tacks, that, we don't go into so much of detail of it. We go into the practical implications of it. But still, it is good to know what we are talking about.
So thanks a lot, ma'am. Thank you very much. Thank you, Garvita, for a wonderful lecture. And thank you, Dr. Krutika, for organizing everything so well.
Thank you so much, ma'am.
I think we can call it a day then.
Thank you. Thank you, all of you. Good
Thank you,
night.
ma'am.
Good night, everybody.
Good
Good
night.
night.